You have probably had this happen. You are deep in a long back and forth with an AI. It has been sharp and helpful for an hour, and then somewhere along the way it quietly forgets something you told it right at the start. Your name. A rule you set. A file you pasted in. It does not say, "Sorry, I have run out of room." It just gets vaguer, starts repeating itself, or confidently contradicts something it knew 10 minutes ago. That is not a glitch, and it is not the model getting tired. You have hit a hard wall that every one of these systems has, and it has a name: the context window. Once you understand it, you will stop being surprised by these failures and start working around them on purpose. Quick note before we dig in. If you find this useful, subscribe and drop a topic you want explained in the comments. Now, let us get into it. So here is the whole idea in one sentence. A context window is the maximum amount of text, measured in tokens, that a model can hold in mind at once. And remember tokens? From 2 episodes ago, those chunks of words the model actually reads. The context window is just how many of them the model can keep in view at a single moment. Think of it as the model's working memory, or better, think of it as a desk. A big desk lets you spread out a lot of papers and see them all at the same time. A small desk forces you to choose. But here's the crucial part people miss. Everything has to fit on that one desk. Your instructions, the entire conversation so far, any documents you pasted, and the answer the model is currently writing, all of it competes for the same fixed space. There is no separate drawer. It is one surface, and once it is full, something has to come off. And that is exactly what goes wrong. When a conversation grows past the window, the model does not magically expand. The oldest material slides off the desk and onto the floor. So the thing you said at the very beginning, the name, the rule, the original file, falls out of view, and from the model side, it is simply gone. It is not remembering and choosing to ignore it. It genuinely cannot see it anymore. This is why a long chat slowly drifts, and why pasting an enormous document and asking a precise question can give you a worse answer than pasting a short, relevant excerpt. You did not give it more to work with. You may have pushed the important part right off the edge. Now, the obvious question: why is there a limit at all? If memory is cheap, why not just give every model an enormous desk? The honest answer, which we will fully open up in 2 episodes when we get to the attention mechanism, is that the cost is not linear. The core machinery of a transformer works by having every token pay attention to every other token in the window, comparing them all against each other. So if you double the length of the text, you do not double the work. You roughly quadruple it. Triple the length, and the work grows about 9-fold. That brutal scaling is why context windows were tiny at first, and why every extra bit of length is genuinely expensive in computation and memory. The window is not small because the labs are stingy. It is small because the underlying math fights back hard as it grows. We will see exactly why when we take attention apart in episode 6. That said, the windows have grown astonishingly fast, and the current numbers are worth knowing because they are part of how you choose a tool. Just a few years ago, a typical window was a few thousand tokens, barely a few pages. As of 2026, a frontier model from Anthropic or OpenAI commonly holds 200,000 tokens or more, and several now reach a full 1 million, which is something like 1,500 pages of text in one shot. Google's Gemini pushes to 2 million. And an open weights model from Meta called Llama 4 Scout advertises a staggering 10 million token window, enough to swallow an entire codebase or a shelf of books at once. The trend line is steep, and it keeps climbing. But here is the warning that matters more than any of those headline numbers, and the labs themselves are careful to admit it. The advertised window is not the same as the window the model uses well. Independent testing keeps finding the same thing. Effective recall falls short of the advertised size on basically every model ever measured. The clearest version of this has a name. It is called lost in the middle. If you bury a crucial fact right in the center of a very long prompt, the model is noticeably more likely to miss it than if that same fact sat near the beginning or the end. The model pays sharpest attention to the edges of the desk and gets fuzzy about the middle, exactly the way you might skim the middle of a long, boring document. So a 2 million token window does not mean you can dump 2 million tokens of junk in and expect perfect use of all of it. It means the room exists. It does not promise the model reads every corner of it with equal care. This is one of the most important practical truths in the whole field, and it is why simply buying a bigger window is not the answer people assume. So, how do models extend the window in the first place? A few ways, and you do not need the heavy math, just the shape of it. Part of it is clever engineering on the attention machinery itself, making that everyone compares to everyone step cheaper to run so longer windows become affordable. Part of it is in how the model encodes the position of each token, the sense of which word came first, second, third, which can be stretched so a model trained on shorter text can stretch gracefully to longer text. And part of it is simply training on longer documents, so the model actually learns to use the extra room. The result is the rapid growth we just walked through. But because of lost in the middle, the smarter move is often not to use the biggest possible window at all. It is to put only the most relevant material in front of the model. And the whole discipline of fetching just the right passages and handing them over, instead of dumping everything in, is called retrieval augmented generation, which is a major part of this course a little later on. Hold that thought. A bigger window and smarter retrieval are two answers to the very same problem. So, how does the context window land depending on who you are? As an individual, it shows up as that slow forgetting in a long chat, and the fix is in your hands. Start a fresh conversation when you change topics so old clutter is not eating your desk, and put your most important instruction near the very end of a long prompt where the model attends best. As a startup building on a model, the context window is a direct cost and design constraint. You pay per token from episode 2, and a giant window stuffed full on every single call gets expensive fast, so you learn to send only what each request truly needs rather than the whole history every time. And as a large enterprise, the window is exactly why you cannot just paste 1 million internal documents into a prompt and call it done. Their knowledge dwarfs any window, and lost in the middle means brute force would fail anyway, so they build retrieval systems that find the few right paragraphs out of millions and feed only those in. The context window is the constraint that makes the entire field of grounding models in private data necessary. So let us bring it home. The context window is the model's working memory, measured in tokens, and everything has to share it. Your prompt, the conversation, the documents, and the reply. It is limited because attention scales painfully with length. It has grown from a few thousand tokens to as many as 10 million, but the usable part is always smaller than the advertised part. And burying key facts in the middle is asking to be forgotten. We have now got a model that reads in tokens, understands meaning through embeddings, and holds a limited window in mind. In every episode so far, the model has been trying to find the single most likely next token. But you may have noticed it does not always give the same answer to the same question. Sometimes it is precise and predictable, sometimes it is loose and creative. That is not an accident. There are dials that control it, and in the next episode we get our hands on them with temperature and top P, the real controls behind an AI's creativity. That is the core of it. If this helped, hit like and subscribe, ring the bell for the next deep dive, and tell me in the comments what you want broken down next. Thanks for watching.